Hi, so my name is Cameron Fenn, and I'm presenting my paper, Forecasting GDP with Recurrent Neural Networks. This paper is joint with Samir Undavia, and it's very recent work. We basically started working on this at the beginning of the summer. Let's go up to the let's talk about the motivation and the general contribution. So forecasting is important for policymakers and private industry. I really don't, I feel like need to go into how GDP forecasting would be useful for central banks, how it would be useful for, government organizations. And of course, it'd be useful in private industry in order to understand how much inventory to hold or widgets to manufacture, right? I think that sort of relatively speaks for itself why the point of economic forecasting is important. But I think the other aspect that I think is not often as talked about is good predictive models can lead to sort of more causal understandings of things. Like, we're not going to argue that our predictive model says anything causally, but our predictive model can learn, higher order correlations between variables that can help economists to create deeper theories connecting different variables, right? And again, we don't have any, theory that, we don't have any, theory that we have derived from these models, but we are working on ways to build these models to make these models more interpretable. And so we can sort of use these models to sort of interrogate these models to understand, more theory, or what is the model picking up that we as economists or as human beings aren't understanding about, forecasting, right? And what do we do? So basically what we do is our neural network outperforms state-of-the-art economic forecasting models for GDP. It also outperforms the median survey of professional forecasters at 5 quarters ahead. Again, I star that just because we only use 2020 vintage data, and I'll get into that a little bit later, but I just wanted to make sure if you don't want to believe our SPF comparisons, you can just compare our performance to the state-of-the-art forecasting models. But what we do, we estimate this model using a cross-section of countries in addition to US data. A cross-sectional dimension gives us power to estimate our recurrent neural network model with 17,000 parameters. We think this is a sort of an interesting approach. It has been done to very limited use in other aspects. But what we basically show is we show basically that we have our single recurrent neural network model trained on a cross section of countries is able to generalize across policy regimes and countries. So a single model can jointly forecast 50 different countries' GDP better than AR models or VAR models, or even our model, but our model wouldn't work for only 250 data points that are forecasting each country individually, right? So we think this model can forecast GDP from countries varying from Latvia to the United States, right? And it can outperform a model trained on just Latvian data or a model trained on just US data. We also do find that other models, like if you allow an AR2, even though the AR2 only has 3 parameters, and you think, adding additional data points might not help that much, especially because, Latvian data points are biased and shouldn't help, forecast US GDP. We also find that when you estimate an AR2 model on this entire cross-section of data, that also increases performance of the AR2 model. It doesn't increase the performance. It doesn't improve the performance of the AR2 model to the point where it's better than the recurrent neural network model, but it increases the performance of the AR2 model. I think it's harder. Our other baseline models that we use are DSGE models and factor models. And again, DSGE model, the Smets-Wouters DSGE model requires about 10 or 12 variables. And so it's difficult, not impossible, we don't think, but difficult. And this is some stuff that we're looking into. Difficult to get a cross-section of like 50 countries having all the sort of Smets-Wouter variables that are necessary. A factor model is less doable. The factor model takes in 250 inputs. So we need a cross-section of 30 or 40 countries with 250 variables, all of them the same across all the countries. We could do a little bit of interpolation and plugging in values, but that is starting to get undoable. However, with our recurrent neural network model, we are able to use a cross-section of countries because we only train on 3 variables, right? We train on GDP, consumption, and unemployment to forecast GDP growth. So our data sources are, we use the World Bank data for GDP and trading economics via Quandl for the other data. Our baseline comparison models, the AR2, the Smets-Wouters, and the factor model, all these baseline models are trained on US data because that's what's standard. I can show you, actually I don't have it with me, but I guess you can trust me when I say this, but the AR2 model does perform better when you train the AR2 not just on US data, but global data. That being said, we cannot train the Smets-Wouters or the factor model on cross-section country data because we just don't have those cross-sectional data available. But nevertheless, these models are typically only trained on US data when we're forecasting US GDP. We train our model on global data and attempt to forecast US GDP. So the test is still the same among all the 3 models. It's just each model uses a slightly different data source, and we're just happy to use whatever data source helps the model outperform the best. The factor model will use 250 different data variables. Smets-Wouter uses, the 11 or 12 Smets-Wouter variables, and the AR2 just uses GDP, right? And we use GDP, consumption, and unemployment, and we also, have, that cross-section, right? And again, the SPF is just, I have the asterisk there because we don't use sort of real-time vintages. If you don't want to trust our comparison to the SPF, just trust our comparison with the AR2, Smets-Wouters, and factor model, which is, an even comparison. We use the 2020 vintage for both estimating these models and evaluating all these baseline models. So the first baseline model, I'm just going to get into like a little bit of background behind these models. We use a linear model, which is 2 lags of GDP to forecast ahead. Despite the simplicity, this is one of the workhorse models among forecasting practitioners. When I say AR2, I just mean autoregressive with 2 lags. That's what the AR2 stands for. It outperforms the Smets-Wouters DSGE at shorter time intervals, but is outperformed by the Smets-Wouters at longer time intervals. A factor model augmented with 1 GDP lag seems to dominate the AR2. There's just more variables, I guess, with the factor model. And so we think, that seems to dominate. Smets-Wouters is a new Keynesian DSGE model that is essentially an extension of Cristiano, Eichenbaum's, and Evans. It's estimated in a Bayesian framework. I'm not going to, discuss the environment, the model, what the optimization problem is, et cetera, et cetera. You can just think of it, if you're not familiar with it, as a sort of black box forecasting tool that uses sort of macroeconomic, that is sort of using macroeconomic theory rather than statistical methodology to build a model. Despite limited attention by practitioners, we think this model deserves more attention, especially at longer horizons. The model outperforms both the AR2 and factor model at longer horizons, but the Achilles heel of this is unable to detect the Great Recession at shorter horizons, which leads to underperformance. Both the AR2 and the factor model can detect the Great Recession coming in, and the collapse of Lehman Brothers is the first quarter of our test set. And so the AR2 and the factor model both get that right, or at least both get that closer to right. Whereas the DSGE model just forecasts 2% growth literally over the whole time frame. I mean, not exactly, but it does not switch regimes when it should. So the other baseline model is the factor model. These models were introduced by Stock and Watson or I guess popularized by Stock and Watson. There are a couple papers and Forney et al. These models take a cross-section of data, in our case, 248 data series, in order to forecast and PCA regression in order to reduce the large cross-section. So it reduced the cross-section of 258 variables into 8 factors. The actual problem is it reduces it to 5 to 8 factors. We estimate this in a pseudo autosample way, and we use an information criteria to decide the number of factors. And so at each time step, it could have a different number of factors. And we do this just for, forecasting accuracy. We want the factor model. We want our baselines to be as strong and robust as possible. We're not trying to hamstring our baselines. And in addition, I think the factor model would already be a sort of formidable forecasting baseline, but we also augment it with one lag of GDP, since likely if you're a forecaster and you're trying to predict GDP, you're not only going to use the factors, but you're also going to add in a GDP, a lag of GDP if you're forecasting GDP. And so we do use that just to make the model more formidable. And it is quite a formidable model. It underperforms over long horizons. And I'll show you a picture of why. You can see exactly where the underperformance is. It's actually one data point. And we think it's likely because of variance issues. Basically, the forecasting model sees a recession coming, and it does a sort of reasonable thing, and it expects a large bounce back. It expects 9% growth in the next 5 quarters ahead, because it's assuming the economy is going to bounce back from this really bad recession. And that's not what happens. The growth is 2 or 3%. And so, over that 1 quarter, it projects a 9% growth, and it's actually only 2% growth. And that just, basically shoots its root mean squared error in the foot. So our model, I've talked about the other models. We use a recurrent neural network as our forecast model, and RNN is a state space model. A Kalman filter is the simplest RNN. It contains a state equation. So that would be this, ST equals A, ST minus 1, B, XT minus 1. The XT would be lags of the observed variables plus C, and a measurement equation, XT equals DST plus EXT minus 1, et cetera, et cetera. So for people who are not really familiar with linear state space models, the state is sort of unobserved. So as the econometrician, you can imagine it's something along the lines of, whether the economy is in a good state or a bad state. And the measurement equation basically tells you GDP is 3%, right? So if GDP is 3%, you can sort of guess that the economy is probably in an okay state. If GDP is in negative 5%, you probably would guess that the state is a bad state, right? And again, this is a little bit of a simplification. Typically, your states would be continuous continuous variables as well. So the problem with a state space model is you have this issue with exploding and vanishing states. Basically, the state can explode. If you write ST plus N, so take N to be a large number, ST plus N, so the state at time T plus N, as a function of the state at time T, it is some equation that is A to the N. So A is the variable that multiplies ST minus 1. A to the N ST plus O of ST. So again, those are just sort of remainder terms, and I'm going to ignore them. But the main problem is you're raising this matrix A to the exponent N, which means that if the eigenvectors of A are larger than 1, then ST plus N will explode relative to ST. But if the eigenvectors are less than 1, then ST plus N will have 0 dependence on ST. Neither of these things is good. One of them is obviously worse. The exploding state would be worse because then your model would just not be stationary when your data is stationary, which would be a huge problem. Is the worst problem, but the other problem is still bad. And typically economists just sort of sidestep and just deal with the problem don't deal with the problem and just forecast with models that just basically have this vanishing state problem, where the state at time steps very far in the future have 0 dependence on states at this time period. So with an RNN, the sort of motivation behind building more sophisticated RNN models, recurrent neural network models, is you want to build a model that can remember long-term dependencies between data, but won't have a state that explodes or returns to the sort of steady state value where the effect of the state has 0 impact on future states. And so the solution of this, ironically, is what's called gates. A gate is a logistic regression with sigma x denoting the logistic link function. And this would just be, your standard logistic regression. This is sort of the standard link function for a logistic regression, or logit, right? These gates output a number between 0 and 1 and are conditioned on the input data, the previous prediction, and the state. The gate tell the model how much of the old state to forget and how much of the new information to remember. So ironically, you're telling the state, you're allowing the state to forget more. You're putting in a gate that makes the state forget more. But what you get in return with that is now your eigenvectors of A can be greater than 1, and you can still be stationary because the logistic gate will have a number close to 0 when the state starts to explode. And so A can take on any value, not just values where the eigenvectors are less than 1. And because of that, the gate can dynamically adjust to keep exploding gradients bounded. People have studied that the asymptotic behavior of states. So what I mean by that is you run the model on data and then you stop running it on data and you just run the model just on its own. So you feed in its own output as the next period's input. And you just run that for, 1,000 iterations, and you notice that the states can be periodic or even chaotic. And the states don't necessarily have to return to what's called like a steady state level. They can behave in any which way. And if you have chaotic behavior, obviously chaotic behavior is hugely dependent on time steps very much in the past. And so you have a model that is able to remember, what the state looked like, 100 time steps in the past, right? There are papers which show that LSTMs, which is one type of RNN, can remember, things that have happened 100 time periods in the past, right? Which is not something a common filter can do. And so the GRU cell. So we don't use an LSTM. We use what's called a GRU, a gated recurrent unit. And so what I don't know, GRU, I call it a GRU. I don't actually know if anyone else calls it a GRU. But I call it a GRU just for the, from that movie, like the Minions movie, not the Minions movie, but the Despicable Me, right? So it's got these two gates. So these sigma G's, these are still the same logistic transform or logit transforms. And you will notice that ZT, or let's do RT first. RT is a gate that this is an element-wise multiplication of the previous state, right? So HT is the previous state. And then ZT is sort of a weighted average. It tells you how much of a previous state to remember and compare that to how much of this sort of first draft of the next state to remember. It's just sort of a weighted sum of these two, and that gives you the next state. Typically, if you're going to forecast a variable like an observed variable, this is the sort of all the equations for the state equations, the set of state equations. If you want a measurement equation, you can add an additional equation that's linear and gives you the measurement variables, or you can make it more complex and add multiple measurement equations or multiple sort of drafts at measurement equations if you want it to be more non-parametric. But again, this is sort of the fundamental what the recurrent neural network is, and this is sort of the centerpiece of our architecture. These W's, U's, and B's are just sort of parameters like the A, B, and C's in the A, B, C, D, E, F in the original example. Yep. Okay, so architecture structure. So I have one more thing to talk about before I this is sort of talking about the architecture structure. I guess I'm going to talk a little bit about dense neural networks. So we also include, so we have our the recurrent neural network is sort of the centerpiece of our model, but we also have a combination of dense nets and dense layers that sort of pre-process the data. The dense net, I'll just discuss that right here. When people mention deep learning or neural networks, I think the prototypical example that comes up in people's head is this image, right, of a neural network. And basically what it is you have inputs. The first layer would be, let's say, a linear regression, and then the linear regression would output a set of outputs. So you can think of this linear regression as a vector linear regression. So a vector regression. It's not a vector autoregression, but it has the same flavor. It's not regressing lags. It's regressing inputs to outputs, right? And then the next layer, the output of the vector regression would be the input to the next vector regression. And you just do this multiple times. I mean, the only caveat here is a matrix times a matrix is still a matrix. So you're still in linear space if you don't do anything except compose multiple vector regressions together. But if you want to, for example, throw in a sigmoid, so you throw in the logistic transform between every vector regression, transforms like this, I mean, are enough to do what is called the universal approximator theorem. So you don't need most transforms, as long as they have the same support as the real world function you're looking at. Many transforms, almost all transforms, non-linearities that people use, can allow the neural network to fit any possible continuous function. So all you need is these compositions of vector regressions, and if you insert in between these compositions a nonlinear transformation, it could even be as simple as, and this is what we use, the max between 0 and the actual output. So the max between 0 and x. So that looks like a sort of a call function, right? So it'd be straight line at 0, and then a linear line going from 0 to infinity, right? This is what's called a ReLU. And we use that in our dense nets. Even a nonlinearity as simple as that, you can show that nonlinearities like that is enough to model any possible continuous function. And this is what makes neural networks so powerful. And so we use these dense layers with ReLU, what do you call them, activations or ReLU nonlinearities. We use that as a way to sort of quote unquote pre-process the data before feeding into the GRU. When I say pre-process, it's sort of an analogy. The whole network is trained end to end. So what happens is the real data, GDP, consumption, and unemployment get fed into this dense net. The dense net sort of projects the data into a high dimensional subspace that the GRU finds easy to work with. And because the whole thing's trained end to end, they give feedback to one another essentially in the estimation procedure. And then the GRU takes this high dimensional projection and comes up with a sort of a forecast of GDP. And the other things we use, standard tricks in the literature, the deep learning literature, skip connections, batch normalization, and we use the atom optimizer. We've tried other things like weight decay and stochastic weight averaging, and I'll discuss a little bit of that later. And so that's just the dense layers of picture. So I'm just going to discuss our results. So we've got a lot of lines here. The dark lines, the ones that are more heavy lines, more thick and less transparent, are the real data, which is this blue line, and then the GRU model, which is this the red line that is sort of darker. You will notice this is 3/4 ahead. So you'll notice that most of these models don't do a very good job at forecasting the Great Recession. It just, but you will notice there is a definite regime shift, right? So like even at this point in time, this is 2008 Q4, these 3 lines from 2008 Q4 to 2009 Q4, the average of these lines is clearly lower than the average over the rest of the period, right? And so there is a little bit of an understanding that, we are in a little bit of a recession regime. The neural network picks that up. The other model that picks up is the factor model. The factor model also picks that up pretty well. And then the SPF, unsurprisingly, somewhat picks that up pretty well as well. You'll notice both the AR2 is not able to pick that up. One of these is the AR2 and one of these is the DSG. I'm not sure which is which. I think this is probably the AR2 and this is probably the DSG. Unsurprising that the AR2 wouldn't pick it up because you only have 2 lags and this is 3/4 ahead. And so, it's probably, you've probably gotten, 1/4 a down quarter of GDP, and it's supposed to predict a negative 8% growth. The AR2 is just not going to do that. The DSG, I guess I'm surprised that it doesn't, but the DSG seems to almost very consistently forecast, 2.5% growth with little deviations. And so there's not much, I don't know, I can't, say anything about that, but, even at lower time horizons, the AR2 is able to pick up the Great Recession, but the DSG is not. And so you can see that our model, the GRU3, seems to, you know, not only get this recession regime well, but it also seems to be less unbiased. I'll show a bias variance breakdown later, but it seems to be less unbiased than a lot of these models, right? A lot of these models are a lot higher in terms of the growth that they're predicting during the expansion. Our model is a lot closer to the mean of the real data, right? Our model is still biased upwards a little bit. As you can see, you know, the mean is probably somewhere here. Our model is a little bit higher, but all the other models seem to be a little bit worse than even us in terms of bias. And so I think the main takeaway of why our model outperforms, it gets the recession slightly, it gets the nonlinear recession slightly better than sort of some of the models. And it gets the sort of unbiasedness of the expansion better than almost all the models, other models, right? And so, and even I think unbiasedness of the expansion is better than the SPF. So this line is the SPF. And I think if you look at the SPF, I can't quite trace it, but I mean, the SPF is pretty good, but again, the SPF still looks like, except for this point, it's a little bit, it overshoots more the GDP growth than our model does. And so these are just, I showed 3 quarters ahead because that was when our model first started outperforming the factor model. You can see here, this is, one of them is the SPF and one of them is the factor model. I think this is the factor model, right? And as you can see, the factor model is predicting a very steep recession. And so it does quite well. At 1 quarters ahead and 2 quarters ahead, it does quite well, better than our model. But the problem with the factor model is it's got very high variance, right? And so even though it picks the recession well, it misses this recession. It's very much forecasting a bounce back 4 quarters ahead. It sees the recession happening in real time and then predicts that GDP will accelerate to 10% because it forecasts. I think, you know, it's very understandable that the factor model would do something like that, that the factor model would say, hey, look, we're in a recession in 5 quarters from now, we're going to have, you know, gangbuster growth, you know, recovery, right? But I think 10% growth of real GDP, even, you know, forecasting for a recession, I think is quite a bit optimistic for the US economy, even if the current recession is at, you know, negative 9% growth, right? It just, you know, that's a little bit too optimistic. And again, our model, you know, at 4 and 5 quarters ahead, our model is no longer predicting the recession at, you know, it's predicting the recession. There's a little bit of a recession prediction, but that amount gets less and less. And basically what it is, it's really just predicting. It's just trying to be unbiasedly, you know, match the expansion data. And so, you know, that's basically our data. And I think it does help that we're less biased to the upside when you get the surprise, the coronavirus surprise, right? Like down here, our model is probably more accurate than all the other models because it's less biased to the upside, even during expansion times. So a little bit on the performance. So if you saw our pictures, you can see the factor model outperforms in 1 quarter ahead and 2 quarters ahead. Our GRU model outperforms the other 2 models, the AR2 and the Smets-Wouters, along all horizons. We only outperform the factor model along horizons 3 to 5. A little bit about these different models. And then again, I guess all our models outperform the SPF median forecast at 5 quarters ahead a little bit. The DSGE even comes close. This probably suggests to me that the SPF probably cares less about forecasting 5 quarters ahead, but also that there's probably more room for model improvement over, you know, humans and what forecasters do now. I think this is sort of the low-hanging fruit if you wanted to improve forecasting in any area or state-of-the-art forecasting, right? And so we have 3 different models. So what GRU model best is, we basically estimated 100 different models on the data. Literally, so with deep learning, you have an optimization problem, but you don't actually find the parameters that minimize your loss. What you're going to do is you're going to optimize your parameters in a numerical way, and you're going to stop optimizing once your validation loss tells you to stop, basically once your validation loss stops improving, right? And so what this means is every time you do an optimization, you get slightly different models. And so we're going to take advantage of that, right? So we're going to estimate this model 100 times over each horizon. The best means we're going to pick the model that performs best on the validation data, and we're going to evaluate it on the test data. So we're not taking the best test data model. We're taking the best validation data model and evaluating it. The other two models is, of the 100 models, we're going to take the mean forecast over those 100 models and then evaluate the root mean squared error of the mean forecast of the 100 models. Same for the median. You'll notice that the best model is always slightly underperforms the mean and median. So you'll see there'll be this underperformance will be even more stark in a later sort of table, but we do recommend that you don't try the best model. You shouldn't be forecasting with the best model. You should be ensembling, and even a mean forecast is probably better. We have some hypotheses about that. I'll get into that later when we get to the section where our best model really underperforms the mean and median forecasts. And so we also do a sort of Monte Carlo simulation. So one of the complaints is, because of this, you have this numerical procedure. One of the issues is, people can say, hey, you have this model that is, 17,000 parameters. It's very liable to have very high variance. You can, run the model 100 times and pick the one that performs the best and report it and sort of cheat on your performance of this model. You can do a lot of sort of p-hacking or model hacking, right? And so what we did here is we just illustrated that we ran the model 100 times, and this mean root mean squared error is different than this mean forecast, in the sense that for this one, we took all the 100 models, evaluated the root mean squared error of each model, and then calculated the mean of that. Likewise, we did the same thing and calculated the standard deviation, right? And as you can see, the standard deviation of all these models is really small. What this means is that when you're doing the optimization procedure, our optimization procedure gets very nearly the same results almost every time. So it's not like if you pick one model, you'll get better or worse performance by a lot. However, and so, this is just sort of illustrating that, it is very, you could very easily reproduce our results by running our same optimization procedure. And it's not just due to like lucky chance that our optimization procedure came across one model that outperformed on the test set really well. Our optimization procedure consistently over 100 runs gets the same result, right? And I think the other thing to note is because of the standard deviation so small, it is even more suggestive, I feel like, that the sort of mean and median forecast you can have sort of, it is surprising that the mean and median forecast is a pretty consistent improvement over the best model. And so I think that's another sort of interesting takeaway, that actually, even though the standard deviation is small, ensembling seems to have a outsized effect. And so here's the model. So here's another robustness check. I think understandably, when we talk about deep learning, people are going to be suspicious of overfitting. It just, that's, I think many economists and many social scientists, many scientists in other fields are sort of suspicious of that. So we're going to say, okay, so we've demonstrated to you that optimization is not going to change your results. Just noise due to optimization is not going to change results. Now let's modify the architecture of our model. So an LSTM is a slightly different model than a GRU, right? Our gated recurrent unit. So this is the equations for our gated recurrent unit. The LSTM is slightly more complicated and is slightly different equations than this, but is also a recurrent neural network. So this is sort of a reasonable change in architecture, right? And so again, our results are still very good. Again, we outperform 4 and 5 horizons. We outperform every model except for the factor model along 1, 2, and 3 on all of these models. And again, our standard deviation root mean squared error, so that is the analog to this, is again the same. Again, I'm not reporting any of the baseline models because the baseline model performance is the same as in table 1. Simply because we did not change the time period, right? We're still using the same test set. And so, And so here's a fourth table, again, a fourth robustness check, right? And so I think people would say, hey, okay, you showed me that, numerical error doesn't change your result. You showed me that changes in the model doesn't change your result. How about if you show me, you change the test set a little bit? How about maybe your model, all these models are overfitting the test set, right? And so here, here our case is less persuasive, but I still think it is very persuasive once I sort of walk you through the results, right? So here what I did is we took data from, instead of 2008 Q4, we did 2009 Q4 to 2019 Q4. And the reason why we took that time period is that has to do with all the expansions. So over that time period, we're only looking at expansions. And I can show you the data actually. Actually, I don't have it here. There are no recessions in this data. So in effect, this is sort of hamstringing our model, right? Because a linear model or a model with less parameters is much more likely to forecast 2% growth every time, right? So like if you are unbiased in your forecasts are going to do very well, right? If you are unbiased in your forecasts are just going to be very accurate, right? Likewise, because we have 17,000 parameters, a lot of that parameter count is used to forecasting when the recession is, because that has huge consequences to mean squared error, right? In the sense that, right, like recessions are sort of much more nonlinear in some sense, not in a very rigorous sense, but just in the sort of intuitive sense, than sort of expansions. Expansions, you're generally always growing at 1.5 to 2.5% a year. Recessions can go from -7% to +5% in a recovery, right? And again, here none of our models perform the best against all these models. However, we will just note that we think our GRU model is consistently performing 1.7. We think that's better than the AR2 model and also better than the factor model when looking at it holistically, right? When looking at it across all 5 horizons. That being said, and we think the mean forecast and the median forecast perform slightly worse than the Smets-Wouters model from a holistic perspective, just because the Smets-Wouters model seems to do, go gangbusters over 4 quarters ahead and 5 quarters ahead. That being said, you will notice our best model performs very poorly. And here is the biggest evidence for why you should use the mean forecast and the median forecast. And we think the reason why the best model, so keep in mind, this is the best on the validation data, right? The reason why the best model performs the worst and performs really bad, so worse than all these baselines by a considerable margin, right? Is because we think what's happening is the validation data contains a lot of data on recessions. Because we got rid of 2008 Q4 to 2009 Q4, we didn't just throw that data away. We thought you couldn't justify that as an out of sample forecaster. We put all that data into the validation data. And of course, that meant it was evaluating models that were good at forecasting recessions. And of course, since by design, this time period had no recessions, our model, of course, would not perform well, as we were devoting a lot, as our validation data was telling our model to devote a lot of effort into predicting recessions, right? Or rather, it was telling us to continue training until we could forecast recessions well. And so, that was the reason that this model performed, we think performed fairly poorly. And again, why we recommend, because of numerical optimization, you're going to get a different model every time you run it. Of course, you can, set the seed and, get a reproducible model. But why not take advantage of that and do some sort of ensembling, run the model 100 times, take a mean and median forecast. If the models get too computationally expensive, and these models are somewhat computationally expensive, they take 15 minutes to run a piece, or 10 or 15 minutes to run a piece, but maybe less, I don't know. But if these models get too computationally demanding, you can always use techniques like stochastic weight averaging that we don't use, but that is something that you can use that allows you to sort of average across different times, or different epochs, what are called, like each iteration of your training procedure, you average across those. And that way you can run estimate one model, but get, hundreds of models to sort of ensemble together. And again, okay, so this is sort of worldwide GRU model performance. So this is sort of another robustness check. So I've showed you, I've showed you the original results. I've showed you the results with a model with the GRU swapped with an LSTM. I showed you results where we changed the time horizon of the test set to show that our model is robust to changes in test set. Now I'm showing you our model forecasting GDP across different countries, so not just the United States. So all this data before was US forecasting performance, if I wasn't clear. Now I'm showing you data where we're forecasting across all 50 of our countries and are comparing it to a country by country AR2 and a country by country VAR1. I cannot use a factor compared to a factor model or a DSGE model simply because the data is hard to find. I can't find data on 50 countries that have, all the required data that the DSGE requires, and I can't find the data, all 250 data variables that the factor model requires. So I have to use an AR2 and a VAR. I use a VAR1. And so what this is basically showing is this is the relative performance. Lower is better. It's just basically a ratio between root mean squared errors. So the GRU is in the numerator and the AR2 is in the denominator. What this says is averaging all the root mean squared errors across all the countries, our GRU has a root mean squared error that's only 97% as large as the AR2 model. So our GRU outperforms along all horizons, all these models. What is also interesting is we don't actually even train this AR2 we don't train this AR2 along the whole data, right? And so this is sort of thinking about the Lucas critique a little bit, right? We train this AR2 country by country as is normally trained in economics, right? So for US data, we train the AR2 only on US data to forecast US GDP in the test set. For Finland data, we only train the AR2 on Finland GDP and forecast on the test set, right? And because we do this and we have checks to ensure that there is enough data for each of these models to perform, adequately. And so because we do that, we sort of demonstrate that we have one model and it's one model that is forecasting jointly all 50 countries. Our GRU is one model, whereas these AR2s is 50 different AR2s forecasting each country separately. And so this is sort of a very, I think it's not a very, what do you call it? It's not a very, we're not saying this is like a central result, but it just sort of illustrates that our model has learned some sort of generalization ability across, you could say policy regimes or across countries. And the reason we do it is understandably because we train it across many different countries. But we imagine, we haven't done this, but maybe I think this is likely for a future paper. But if we train it on 49 countries and then estimate it on the 50th, we think our model would do pretty well on that. Of course, not amazing, but we think it would learn some policy and variance. And so this is sort of a first crack at answering, or maybe not a first crack, but at least best to my knowledge, a first crack at answering the question, what is more important for sort of satisfying the Lucas critique and ensuring things are sort of policy invariant? Do you need data, better data, and data that is, data that goes across many different policy regimes? Or is it more important to have a structural model that is sort of by design resistant to the Lucas critique? And I think our GRU model shows that you can have a reduced form model that is very sort of resistant to the Lucas critique if you give it data that allows it to generalize. If you give it data across many different countries, it will be able to generalize across many different countries. So we did sort of test a little bit. I don't have these results here, but we did try to test an AR2 that's trained on all 50 countries simultaneously, just like we trained the GRU. That actually improved the performance of the AR2, but it didn't improve the performance of the AR2 better than our GRU model. These GRU models, especially, and so we hypothesized that. Oh, I'm going the wrong way. We hypothesized that our GRU, this training procedure can be used to also improve the performance of DSG models. If you get, a cross section of 50 countries and estimate a DSG model across all 50 countries, we think the Smets Values will have better forecasting performance than it currently does. We haven't done it. I'm not a big DSG guy, and that may be something to tackle. But if someone else wants to do this, I don't really, this is not a huge priority for me. And, I welcome whatever other people to do that. If you want, you can tell me, and I won't write that paper if I'm thinking about it. But that's just something to like sort of approach. And we think, that I think me and Samir are pretty confident that a DSG trained on, 30 or 40 countries, that data will outperform the Smets Values DSG. We think that's very likely. And so the last thing is just forecast bias and variance. There's not much here that I, would like to talk about other than our GRU seems to be less biased than every model except for maybe the factor model. And so this is really a test of forecast bias. It's like a statistically significant test. So we have the standard errors and we have basically the bias of the model. How we estimated this is we literally just, we took, true data minus, forecast data and took the average of that and took the standard deviation of that. And we basically, constructed a statistical test for if the model was statistically biased. As you can see, a lot of these models are statistically significantly biased. The GRU is somewhat biased and the factor is less biased than all these other models. And then interestingly, because we calculated the standard deviation, that's very much related to the variance. It's not, quite the variance. Obviously, you have to square it and so on and so forth. But these parentheses terms are sort of a proxy for the variance of the model. And as you can see, our model has lower variance on a holistic level than all models, except for the SPF probably. And so this is how our model outperforms. It's less biased than all the models except for the factor model, and has less variance than all models except for the SPF. Here I noticed there's not like a sort of additive relationship between the two. To get root mean squared error, you'd have to square some things and do a couple other things. But variance, small drops in variance account for more outperformance in root mean squared error than drops in bias. And then, so just the conclusion, our neural network forecasting model was competitive with the best economic forecasting models. As neural networks have many architecture choices, we plan to add even more state-of-the-art improvements. With the suggested evidence of policy invariance in future work, we plan to use these models for counterfactual analysis. And then, that is basically the end of my presentation. Thank you very much.